Alright, let's go to a matrix vector operation, right? So what's a simple matrix vector operation? So you have a matrix A. For simplicity, I'll take it to be n cross n. And let's say you have a vector x, which is n cross 1. And you want to compute ax equal to y equal to ax, right? So I want to multiply a matrix with a vector. How do I distribute the work? What is the simple code for this? So I'll have a loop for I equal to 0, I is less than n, I plus plus. J equal to 0, j is less than n, j plus plus, and then I say y of I plus equal to fine. I am assuming I have initialized yi equal to 0 outside, right? So this is the operation I want to perform. How should I distribute this work? What's a good way of distributing it? So don't look at the code when you want to distribute it, like look at the problem. How would I like to distribute this work amongst the threads? So let me start with one very simple one, right? Let me distribute the columns of A. What happens if I distribute the columns of A amongst the threads? So let's say thread 0 takes care of this column, thread 1 takes care of this column. So what will it do? What will thread 0 do? It will multiply this element with this element, and that result will have to go here, right? But that's not the complete element of y that we want. That's just a partial answer, right? And then what will thread 1 do? It will multiply this with this and add it to this, right? So these threads have to basically combine their results, right? And then thread 0 would also go and pick up this second element, multiply it with this first element and store that here. And then thread 1 would also do the same, multiply this by this and add it over here, right? So what's wrong with this approach? What's good about it? What's bad about it?
We have to lock one thread when one is writing into a particular element of it.
So if all of them need to write to the same location, right? And that too very often. Every time you have to go and update an element of y, just you do one multiplication, one addition multiplication, and then you have to go and access one element of y, and for that you have to lock it because others are also trying to do operations over there. What other issue is there with this approach? So have you guys worked with C or Fortran? C. Anybody worked with Fortran? You worked with Fortran. Okay. So there's a basic difference in the way matrices are stored in C and Fortran. Okay. So you have to be very careful when you're coding up, particularly, I mean, if you're used to one, then you know about it. So the way C stores the matrices is that it stores them in the row major order, right? Which means that if this is A11, A12, A13, A21, A22, A23 and so on, in physical memory does not have a matrix structure, right? Obviously it's just a linear, you can think of it as a linear structure. The addresses are arranged linearly. So A11 would be stored at some location, right? Whatever this location might be, maybe address 1002, and then A12 at the next location, and then A13, and then A21, and then A22, then A23 and so on, right? That's the way C stores the matrices. And how does Fortran store the matrices? The other way around, right? Column major order. So Fortran would store it as A11 followed by A21 followed by A31 and then A12 and so on. Okay. So why is this important for us? Thread 0 is working on this column. In C, how is this column stored? It's not contiguous. A row is contiguous, column is not contiguous. In C. In Fortran, the column is contiguous, right? So, but we'll stick to C for now. So, the column is not contiguous and that is a problem, right? Because these data accesses, every data access is going to require a hit to the memory. It's not going to find it in the cache, right? Let's study the other approach. Let me pick up a row of A and multiply it with the column of X, and what will I get? I'll get the first element of Y. So this is contiguous. A vector is always contiguous. I mean, whether it's a column or a row doesn't matter. A vector is a vector. It's always stored contiguously. And what's good about this approach? Well, you are accessing this row also contiguously. So you're getting the benefits of streaming. This is contiguous, yeah. And each thread is writing to a separate location of Y, a separate element of Y. So he has ownership of what is being written into. So you don't need locks, you don't need critical sections. You can't always do it, depends on the algorithm, but one of the basic things you should try to do is divide the work given to different threads based on the output, where they have to write. Because if you can separate out the regions where they are writing, then you can get rid of a lot of locks and overhead of locks and critical sections. Okay? But when you run this code, you'll be surprised that you're not getting very good performance. There is one basic problem over here. What is that? So let's look at two threads, right? So let's say the first thread is working on row 1, the second thread is working on row 2, right? Well, both of them are accessing X, that's not an issue. When multiple processes are reading the same element, right, reading the same data, it can be fetched into their local cache. The only problem comes when any one of them writes to that data. Remember the cache coherency protocols, right? It has to go and either invalidate or update all the other caches, right? So problem comes with writing. With reading, there's no issue. If everybody is only reading data, it will come into each one's cache and reside over there. No issues at all. Okay? So what happens over here? So this is processor 1. This is processor 2, right? And he has his own cache, he has his own cache. So as far as A and X is concerned, right, there is no issue. They are only reading these and they are reading them sequentially, not an issue. Here's the problem that will happen with Y. When processor 1 reads Y, right, it's going to load up in its cache somewhere. So it's updating Y0, right? But unfortunately, what you get is a cache line, you don't get an element. So what has come into its cache? 4 elements maybe, right? Depends on the cache line size and the data size, but if you have an 8-byte double precision floating point number and a 32-byte cache line, you'll get 4 elements. So what has come into the cache? Not just Y0, but Y1, Y2, Y3. All of them are in the cache of processor 1. Now processor 2 starts working. It's going to fetch Y1 over here, and when it fetches Y1, it's going to automatically fetch Y0, Y2 and Y3 also. The same cache line is going to come in both of them. Okay? Now the moment processor 1 updates Y0, what's going to happen? Although it has not updated Y1, yet it has touched that cache line, and whether some data has been updated or not, or is dirty now, that is kept track of at the cache line, not at the element. Okay? Because the cache doesn't know what is the data you're storing in it. A cache only knows that I have a 32-byte line. That's all it knows, right? So you have touched some data in this cache line. So the cache says that this is dirty now. This cache line is dirty. What's going to be the implication of that? the cache coherency protocol kicks in, and it goes and, let's say, invalidates this cache line which processor 2 was working on, right? And then processor 2, when it tries to update y1, it's going to make this dirty. What does it mean to invalidate the other cache line? It means that the next time processor 1 wants to work on y0, it will have to again go and fetch it from the memory because its data has been marked dirty. So either you are invalidating or you are updating. In case of invalidating, what happens? Whenever you update your value, you go and mark all those caches where the same line is loaded, you go and mark them as invalid, which means that the next time that processor wants to access that data in that cache line, it's going to have to go to the memory, right? In case of updating, what do you have to do? You have to actually send that data. You have to send that data to all the other caches where that cache line resides so that they can update the local caches. So you're getting the issue. In both cases, there is a lot of overhead of synchronization. So this is something called false sharing. Okay? Even though you're not sharing the data, but because of the cache line size being large, to the architecture it seems that you're sharing data. Both of them are trying to access that data and marking it dirty, right? So there are multiple ways of dealing with this problem. One is that just store it in a local variable and update it at the end, right, into y0 or y1. Update it only once, yeah.
Why the processor 2 cache will be having y0? It will be having y1, y2, y3, y4 because it is going to update in the memory location of from y1.
Yeah, so the way the caches work is, if your cache line size is 32, then the only entries that you can store are address 0 to 31, address 32 to 63, and so on, irrespective of which data in that you are accessing. So even if you are accessing this data, the cache line it will load is 32 to 63. So all addresses start from multiples of 32 byte offsets. Okay? So how do you deal with this problem now? So there are multiple ways of dealing with it. One is that you could store the result in some local variable, private variable, and then at the end you go and update y0, right? But that's not the way you want to work, right? That's not very natural. Sure, you can do that. That's one solution. And any other solution? Anything else you can suggest? So here's what you can do. You can say that let me allocate the first maybe 10, 12, 16, whatever, right, rows to thread 0, next to thread 1, and so on. So I'm talking about large matrices over here, right? So I could just again use a dynamic schedule and divide it into chunks of maybe 16 or something and work on 16 rows at a time, right? And let the runtime figure out that how it's to be divided amongst the threads, right? How would the code look like? This is what the code looks like, right? So I add a hash pragma omp parallel for with schedule as dynamic, right? What is this I? This I is nothing but the rows, right? It's a row number. So I can just say dynamic comma, let's say 16, right? Okay, so that's enough to parallelize this matrix vector product. That works well. So there's always some false sharing that's going to happen, right? You can't completely avoid it, but you should try to minimize it as much as possible. If you know that there are simple tricks to avoid false sharing, then you should definitely employ. So here also, I mean, at the end of the day, after you have allocated 16 elements of y, right? You don't know whether that's at a 32-byte boundary or not, right? That this may be in the middle of a cache line. Maybe this cache line starts here and goes up to here, right? So there may be some false sharing. So if you want to avoid that also, then you have to ensure that your entire array starts at a 32-byte boundary so that it starts at a cache line. So there are ways of doing that in C, right? You can specify those things. And then ensuring that the chunk size that you have specified is again an amount of data which is multiple of the cache line size. So you can do all that if you want.